Good afternoon, everyone, and thanks for attending my talk. So, as I was presented, I am Adrien Mau. I'm a photonic engineer at Abbelight. And today I will present to you laser illumination, so in classical and in super resolution multicolor microscopy. So, laser illumination is a really critical aspect in our field of microscopy, and it's also something that we are exploiting, as mentioned in with the Laserlab-Europe, on especially in a European nanoscan project with many collaboration with researchers such as the Poligny Center, CNRS, and CNR. So today I will focus on the technology that my company Abbelight is developing. First, I will start with introducing briefly my company. So our vision at Abbelight is to push the boundaries of scientific discovery by integrating everything that is innovative and that is new and that is useful in research. We try to grab, to comprehend it, and then to make it available to everyone worldwide by a easy to use and comprehensive workflow solution. So typically, we don't only do microscopy imaging, we also handle sample preparation, imaging, and data analysis. On the solutions that we can propose today, so it's a complete workflow. We can use reagents for the sample of a biologist. We can do fluidic automation systems. Obviously, today I will focus more on scalable and easily upgradable imaging platforms, so on the technology that we use in the imaging parts, but we also have a software suite for data acquisition, automation, and analysis. On Abbelight, so we do microscopy, but we do microscopy to nanoscopy. So we can either image live on dynamic cells, so living biological sample. Here we use a microscopy that is fluorescence microscopy, so it allows us to see specific parts of the sample. Here, for example, you have clatrine, but on the right side, you have microtubule of the cell on the mitochondria. So we can do this in live on a microscopic scale, but we can also work on fixed cells to get nanometric scale imaging, so in the order of 10 to 20 nanometer resolution. And the company is rather young, so as you can see here, we have a roadmap of our technology. We started by implementing the TIRF on the SMLM, which is a super resolution technique, so a nanoscopy technique. Then we made it 3D on. Then we went out with a technology named ASTER that I will focus mostly on today. But I will also present to you multicolor microscopy that we did with the spectral demixing technique. And then the list is going on. We also have an ongoing project with nanoscan with the ASTER technology. So just to introduce a bit the field for those who don't know it very precisely, fluorescence microscopy is, a microscopy, you guess it, that use fluorescence. So typically, if you look at a fluorophore like Alexa 647, it will be able to absorb light that you shine on it. So it can be white light or laser light. And then it will emit some wavelength back. So it's a bit random which wavelength it will emit back, but it will emit wavelengths which are higher. So it will lose some energy. And because of this, if you use a laser, it will be exactly adapted to this kind of technique, because you can shine a laser at one specific wavelength which absorbs very well. And then you can use a filter on your imaging path so that this laser does not go to the camera, and only the fluorescence part goes back to the camera. So this is extremely useful because then we can bind these fluorophores to a sample. So typically we can attach it to an antibody and look only at microtubule, look only at mitochondria, look only at clatrine. So this is a bit of the scheme that I show there. You can shine, for example, a green laser, and then you will get a fluorescence emission, so bound to mitochondria that is mostly in the orange or red parts. And typically, we will focus the laser at the back focal plane of the objective. So this will yield a collimated and wide beam at the sample part. So this is very useful, but when I started my PhD, and when also Abbelight started, there were big limits of laser illumination in microscopy. And typically, one is due to the Gaussian shape of lasers. So lasers will have high intensity at the center and very low intensity at the side. So what happens is that if you shine a laser at a sample in fluorescence microscopy, you get inhomogeneous signal on noise ratio. You lose some power at the side because you're not going to do anything with the power at the side, and you cannot quantify your data because of this. A second disadvantage of lasers was their coherence. So they can interfere with each other. And typically, if you look at a sample with a high angle, you will see this kind of interference fringes on the left, while the real sample that you should be seeing is this one on the right. So we wanted to tackle this issue. In order to do this, we developed a novel technology which named ASTER, so adaptive scanning for tunable excitation regions. You can look it up on Nature Communication. So the base idea of this is that usually people will can either have a wide Gaussian beam at the back focal plane of a lens, which will give a small Gaussian beam at sample plane, or you can have a very focused Gaussian beam at a back focal plane to get a wide Gaussian beam at sample plane. And typically, because it's inhomogeneous, you will only keep the part that is at the center, which is relatively flat. But then we have an idea what happens if you have a small Gaussian beam at sample plane, but then you go with different angle in the back focal plane so that you can have close Gaussians next to each other. So if you do simulation, you will see that the field obtained by superimposed closed Gaussians can be in fact relatively homogeneous. And if you do that in 2D by scanning a beam, the temporal average that you will get, so each part of your sample will get actually a homogeneous illumination. So we wanted to test this in experimental manner. And to do this, we started from a laser source to send it all the way to a sample. So by focusing at the back focal plane of the objective. And now you can focus your attention on this part, which is 2D galvanometers. So here we have scanning mirrors, which allow to send the laser on the right or on the left of the sample as we want. So you can see everything is perfectly conjugated. And if you do this, then the scanning on the back focal plane, so you can actually get something homogeneous. Here we image a thin layer of fluorescent sample, so night blue. And instead, wait, just want to launch the video. So instead of starting with a wide Gaussian beam, we use a smaller Gaussian beam at sample plane, but we can move it around with scanning. So we can move it left, right, or up and down. And then, of course, if we start to scan very fast compared to the integration time of the camera, we can do a line, we can do a square, we can move it around. And we can do actually, because we're just controlling electronically, we can illuminate with a square of any size. So if we look at the profile that we get on a night blue layer, we get something that is much more homogeneous than a Gaussian. And then, of course, you have some Gaussian border at the end, and you are also limited by the objective and the optics that you use. So this was great. We got a uniform illumination, also tunable, but there was one more thing we wanted to do. It's optical sectioning. So typically in fluorescence microscopy, because you image the sample in a conjugated manner, you will illuminate all of your sample with the laser, but you only need actually the part that is in focus to be illuminated. Everything that is out of focus will add some background noise. So what people do is usually you shift the beam in the back focal plane of the objective so that it gets out with a typical angle. So in the same manner that a different angle in the back focal plane gives a different position, here if you change the position, you get a higher angle. And like this, you can only illuminate the part of the sample that is in your field of view and not illuminate the part in depth. Then if you go with a very, very high angle, so actually higher than 90-degree output, you get a specific physical phenomenon, which is named total internal reflection. And your sample is only illuminated by an evanescent wave very close to the cover slip. So only at the part of the sample that stick to your glass cover slip. So like this, you can image very specific parts of cells, like the protosomes. And we do this effectively by shifting, here you have a little animation, the beam in the back focal plane of the objective. So what it will give you on cells, so ILO is an equivalent of oblique imaging, is in EPI, you have your whole cell image with some background. In ILO, you get an intensity boost and you have a bit more optical sectioning. And then in TIRF, you only see the part of the cell that is stuck to the cover slip. And we wondered, is ASTER also able to do this? So it would be very interesting to be able to do it, but it was not obvious. So actually, compared to a classical Gaussian beam, which is inhomogeneous illumination, we were already able to do epifluorescence or collimated illumination on a wide field. So you can see that it's pretty homogeneous. Here we're looking at mitochondria of the cell. And if you look again at our optical setup, you can see that we use a TIRF translucent stage. And this is actually able to move the part of the beam that is focalized from right to left. So in a conjugated plane at the back focal plane of the objective, it will move the beam right and left, and it will add an angle as you want. So then we tried it simply. So you can see here that we will still illuminate the same part of the sample, but we will add an angle, and it worked. So you need to have a very good optical alignment, but in the end, you could get uniform illumination on a wide field with optical sectioning. So we were very happy with this. On top of that, we noticed, so probably due to the scanning effect, that we had no interference pattern from the laser. So this was great, but then we noticed that if for us opticians, it's easy to set up TIRF and ILO on specific angles, it was not easy to do it in a reproducible manner and to be robust. So we went on to do a quantification of the TIRF, so and also a calibration. And then you can get this kind of image where you see the intensity that you get depending on the position of the back focal plane, so depending of the output angle. And then when you reach the TIRF range, we are able to say what is the penetration depth so how deep you will be able to still illuminate the cell depending on your position. And here you can see you have the ILO illumination, and then you have a TIRF illumination at various penetration depths. So to conclude, with this, ASTER was able to yield homogeneous illumination to improve optical sectioning, but also on top of this, we get a flexible and tunable power distribution at sample plane. So this was all done in a Widefield classical fluorescence microscopy, but our company, as I mentioned, focused a lot on a super resolution technique, which is named single molecule localization microscopy. So compared to classical image that you will get, so here we're looking at extracellular vesicle, which were deposited on a cover slip. We have a technology that is able actually to super resolve this thing, to see that they are actually hollow and not just blurry spots. So how does it work? So typically, if you try to image something that is very small, you will have an issue with the fact that it will leave a diffracted spot at your imaging plane. So it's named the diffraction limit, and it's usually in the order of 200 nanometers. So if you have two close emitters like this, you're not able to tell from the blurry spot that you get. You cannot tell if there were two of them or only one or three or five. But then a technique came around 2015, which is named SMLM, and it relies on a blinking process. So blinking is really an essential part of this single molecule techniques. So it can rely on photochemical reaction and photophysics typically used with lasers. And it allows us to not image all fluorophores at once, but to have them emit sequentially one by one in a random manner. So why is it useful, you may ask? It's useful because when you have a single emitter, so this single blurred spot, you are actually able, even if the size of this spot is 200 nanometer, you are able to do a fit. So try to find, for example, the Gaussian shape that better adjusts the image, and you can, like this, estimate the center of this emitter very precisely. So it's named the localization precision. And if you do this, you get localization precision in the order of 10 nanometer. So if you localize millions and thousands and millions of fluorophores like this, which are isolated by the blinking process, you can generate an image by reconstructing a point cloud of localizations. So this is a great technique. It won a Nobel Prize, but it's still hampered by Gaussian illumination. So typically, in one of the blinking process, which is named D-storm, you will get inhomogeneous blinking because of this Gaussian illumination. So as you have very high intensity at the center, you will blink very quickly. So you can get isolated molecules that you can localize. But at the periphery of your field of view, because you have less power, you have a worse blinking process, and you cannot really distinguish emitters. So you cannot localize an emitter one by one. And typically, if you look at your final image, you will have a very clear, very sharp image of microtubules here, where the crossing between microtubules is very clear. But as you get far from the field of view, it becomes blurry, and every time you have crossing of microtubules, your image has artifacts. So if you also want to quantify your blinking, for example, measuring the number of photons, so here is a colored map of the number of photons that the fluorophores emit. You will see that it's very high at the center, but very low at the periphery. And then we used calibration sample, which is named nanorulers, to better estimate the localization precision of our link with this illumination. And we found that you can localize molecules, so with precision of 6 nanometers, 7 nanometers at the center, which is very good, but it's only on a very, very small field of view. As soon as you get away from this center, you have very degraded localization precision, up to 10 nanometer, 12 nanometer. So then we tried to calibrate with nanorulers with ASTER, and we found out that if you look at a map of localization precision like this for each nanoruler, if you, for the same field of view approximately than the Gaussian one, ASTER can yield uniform localization precision of 7 nanometer on a whole field. In general, all the nanorulers will be better resolved. And if you keep the same laser power, but you get a higher field of view, you get a slightly worse localization precision of 9 nanometer because you have less laser power, but still you're able to image on fields which are maybe 20 times bigger than just the center of this Gaussian. So this was really great, and we found out also that because we are very efficient in the power that we send to the sample, we are actually able to get much bigger field of view than what is usually done in the field. So typically people will image only 40 by 40 micrometer of field of view, but with ASTER on only 200 milliwatt, we were able to image a 200 by 200 field of view of microtubules. So compared to what was done by the field at this time, they were using mostly like 2 watt or 4 watt of laser power, which can do a good blinking, but will also burn your cell at some point. So ASTER really has this flexibility in terms of shape of the field of view that you image. And typically, because you have to integrate a lot of localization, so millions of them, in single molecule localization microscopy, your imaging time for one image can be 30 minutes to 1 hour. But if you concentrate the power, we found out with a publication actually from researchers always, that you can get a faster blinking. On here, what I'm showing you is reconstruction of microtubules a long time, and you can see that already after 20 seconds, we were able to get an image of the microtubules on this whole field. So really, by concentrating the laser power, if you don't want to image a big field of view, but you're interested in a specific part of your sample, you can use the tunability of ASTER to do precisely what you want. To finish, I will present a bit how we do multicolor nanoscopy. So here are example image that we do in 3-color nanoscopy. And typically, this can be a bit hard to achieve without crosstalk. So the usual method that is done in multicolor microscopy and nanoscopy is to associate one color per structure. For example, if you want to look at microtubule on clatrine, you will use a red laser on a red fluorophore bound to microtubule, on a green laser on a green fluorophore bound to clatrine. So you do it sequentially, but then in nanoscopy, typically you will get chromatic aberrations. It's something that we cannot notice in our everyday life because it's a very small effect. But if you try to image, for example, a microtubule that is labeled both with a green and a red fluorophores, actually the green image on the red image will not be superimposed. So you can see here, it was shown by Clément Cabriel, that you have a shift of around 70 nanometer in the Z position. You can also have a magnification shift. So in nanoscopy, it will be a problem. You will have to calibrate it every time. But also, if you do a sequential acquisition, you have to use different fluorophores. So you have a different blinking process. You can have a big temporal shift of the sample between the two acquisitions. And it's also costly because you need one laser per structure or per color. So what we wanted to find is if there existed a method that could use dyes with close spectral emissions that could then allow us to use the best dyes in a storm, which is the blinking process. So we wanted to do it simultaneously with a single laser on a single set of filter. And then we opted for the technique, which is named spectral demixing. So it was used a lot already at the time, you can see. And it relies on a simple process, actually. If you take the example of one fluorophore in red and one in the far red, so IF647 and CF680, you can see their spectral emission are very close. But if you add a dichroic on the detection part, you can send the higher wavelength on one camera, on the lower wavelength on the other camera. And if you do so, then on the first camera, IF647 will be much brighter. On a second camera, CF680 will be brighter. So just like this, you can distinguish between different fluorophores by calculating a photonic ratio, which is typically the number of photons on one camera divided by the total. So then I can show you a typical experiment that we will get. So here you have the two camera frames with, and we have image two colors. So it's mitochondria on the reticulum, endoplasmic reticulum. And you can see some fluorophores are brighter on the right camera, the reflected camera, and some fluorophores are brighter, typically the lower one on the left camera. So the blinking process will look like this on a whole field of view illuminated with ASTER. And our software, so then we will localize in live all the molecules that are blinking, and we will calculate the number of photons which were on one camera compared to the other. And it will yield a photonic ratio, as you're seeing on the right, with a lot of molecules associated obviously to one population and the other molecules associated to the other. So if you filter on this, then you're able to reconstruct a population of endoplasmic reticulum in yellow, and then a population of mitochondria in purple. So this is an example of what you can get after a 5-minute experiment in live, so in multicolor nanoscopy. Then I will go a bit faster, but we are also able to combine this with true 3D imaging. So this is a bit specific. We had a specific lens in our sample to do this. So here it's clad-twin on microtubule. You can see both can be well isolated. And then if you travel in the sample in 3D, you can see these microtubules which are going up and down of each other and are well separated. So to conclude, our technology in imaging includes a novel illumination technique, which was developed at the ISMO lab. So it's named ASTER, which allows to get a flexible, uniform field of view. We also deliver quantitative optical sectioning, notably with TIRF, and spectral demixing technique, which allows to get fast and high-quality multicolor imaging. And this, obviously, is all included in our products. So the part I talk about, the ASTER part, is actually only this little module there. And then we have a lot more to present. Notably, this is a detection path that you will use in imaging. And of course, you also need a microscope. So we are always pushing the limits on developing new technology. Notably, I mentioned the nanoscan project, where we will use ASTER with super resolution techniques. So thanks everyone for your attention, and don't hesitate if you have any questions.